Good day to all our participants who have joined us for today's lecture. My name is Lynn Seholster from CDC in Atlanta, Georgia. On behalf of Dr. Syed Sattar and Paul Weber, I would like to welcome you all to another presentation in the Weber Training Teleclass Series for 2015. Today's speaker is someone well known to the teleclass audience. He is Andy Streifel from the University of Minnesota in Minneapolis, Minnesota. He's made my job as today's hostess very easy given the information on his second slide, but I'll add that he is based in the university's Department of Environmental Health and Safety. His topic today is ventilation for energy management and infection prevention. So, without further ado, let's welcome Andy Streifel because he has a lot of good information for the audience today. Take it away.
Thank you so much, Lynn and Paul. I greatly appreciate the opportunity to do this. I've done this a half a dozen times at least in my years, and I appreciate the opportunities that I've had here at the University of Minnesota. On the first slide, you see that we have a couple million square feet of medical complex, and certainly that has been my laboratory to participate in infection prevention issues as well as industrial hygiene issues in our institution. And the second slide gives a brief summary of my tenure. I visited many hospitals. I participated with Lynn and others at the CDC and greatly have had wonderful opportunities to provide guidance in infectious disease and some of the design issues. As we look on to the third slide, we really recognize what Dr. Mamazadeh has said, a very wonderful scientist at NIH, saying that we certainly could improve our energy efficiency in the rooms in the hospitals. And you will see we are a very utility-intensive industry, and as the slide moves on to electrical usage in a Houston hospital, certainly look at the ventilation fans. It consumes about 24% of the energy for the electrical energy for this particular hospital. It's $1.4 million. It's a great percentage of that, of 20-30%. And certainly that's the goal of what we see in many hospitals is to get the ventilation, get the energy costs down. And we have lofty goals of trying to save 20% of our energy costs here on campus over the next few years. And if you look at slide 5, you see real quickly that the reheat. Now, what you ask, you're thinking to yourself, what does reheat mean? Well, in ventilation industry, we generally speaking deliver air, roughly for those of you who are Fahrenheit minded, 55 degrees Fahrenheit, and we heat it up to whatever temperature we want on the local reheats. That's expensive. We're going to talk about ways where we can reduce that cost and really apply it in a good infection prevention method for enhancing the safety, internal safety of the hospital. So we have goals of trying to reduce gas consumption, reduce electrical consumption, and we always have to remember that it's about the patient. Slide 6 has the unfortunate group of severely immune-compromised patients that we have in some of our facilities, but we treat all our hospitals basically the same as areas for a sanctuary for convalescence and recovery from terrible diseases in some instances, and in some instances just simple diseases or injuries. So we need to remember always that it's about the patient, and we certainly want to balance what we do from an energy efficiency point of view and a patient safety point of view. So what drives high energy use in healthcare? Right on top is ventilation. It's mainly because we insist that we highly filter that environment. If you look at the total industry, we really are industry that has highly filtered buildings, way higher than what we see in most of our commercial space. In addition, our indoor air quality standards generally mean we have to have 12 to 20 air changes per hour. In our operating rooms, we even exceed that. So it's really there for waste anesthetic gas management. Heat gain. Heat gain is something that quite remarkably requires us almost to cool all 12 months of the year here in Minnesota. And if you look at the electrocautery smoke from Bovie, the Bovie gadget, it generates a huge aerosol of smoke, and we need the air change rates to knock that down, as well as the some surgical shedding in surgical aerosols. Really, there are no standards, but we know good and well that you have to cover up in order to prevent a lot of that. Airborne infection protective environments, high air exchange rates, exhausting directly to the outside, temperature control, humidity control, minimum outdoor air for freshness. In addition to all the other things listed there, we really become an energy-intensive industry. And when we look at the diseases and the statistics, how concerned we are about healthcare-acquired infections, pneumonia makes us think that there might be something associated with the air, but we know better than that. Airborne spread diseases are out there. We certainly recognize them in our world, and we do get paranoid about that, but yet we have to realize that we can do a lot to protect our loved ones in the hospital, our clients, our patients, and we do that when we look at the slide that says factors involved with the spread of disease. Droplet nuclei transmission dynamics are really remarkable. Those droplet nuclei, tiny things, less than 5 microns, follow the wind currents, the air currents of the building and move around. The nature of dust levels. Now, what does that mean? I've seen incredibly dusty hospitals and incredibly clean hospitals, and they both have problems. So you never know exactly what the issue is, and we will explore some of those in the minutes to come, and even consider the fact that our patients, again, being immune compromised with dry air and potential embedding of infectious agents into the mucosal lining might give them an opportunity to grow. Population density and ventilation certainly play a part, and from some of the ICUs I've been in lately, my gosh, are they crowded. So our diseases spread. I think a lot of it has to do with the technique and the protection. We certainly need to protect ourselves with standard personal protective equipment, and that principle of early detection is paramount in our ability to recognize and isolate before that secondary infection starts to show up because of occupational exposure. And we do need to have the SOPs. We've seen a failure of SOPs in this year with the Ebola problems that have shown up here in the United States as well as elsewhere. We need to be ready to understand how to use our PPE, what disinfection strategies work, and, of course, that appropriate ventilation design to move us forward. And in slide 11, on looking at indoor air quality, we have to think beyond, if you will, the infectious agent. We need to think of those chemicals. We are an environment. Hospitals are an environment, or is an environment of controlled hazards. So we certainly recognize that the air could have some of those, and while we like to think infectious particles are paramount, we also have chemicals. We also have a variety of other things that set us off, especially odors. I have to respond quite a bit a lot of times to odor complaints within our facility in an effort to, again, to better understand what we're up to and what we need to deal with. But of course, when we look at the infectious diseases that are spread by air, there aren't that many really that are well documented. Aspergillus and mucorales from fungi, we certainly are seeing more mucor in certain patient populations of late, and why. Lynn and I can speculate a lot on that, but yet we start to see that. Tuberculosis, of course, worldwide. Measles, we've had little clusters here from folks who come to us from other countries that haven't had the vaccine. So we certainly see those things with some regularity, as well as some of the other uncertain but yet potential spread organisms. So suffice it to say, we need to think about all our infectious disease management principles to control those droplet nuclei through interrupting that chain of infection. And we need to do that in a way that is proactive. And if we look at the fungi that show up in our hospitals, the one on the upper left from my hospital, due to poor ventilation management, poor humidity management, leaky sinks in the bathrooms and pharmacies on the lower left, where manufactured drugs are an essential part. And if you even look at the other with it all over the walls, that's a failed pressure valve that we found in a autoclave room, a mechanical room. So these things are all capable of getting into the air once they proliferate and produce those spores. And of course, a lot of these spores are smaller, or about the same size as droplet nuclei, less than 5 microns, and they are aerodynamically capable of moving around on the wind currents, the air currents of our hospitals. So we are aware of that, and it does have a devastating effect. If the papers that have been published by various people from around the world showing the incidence of a variety of patient types who get aspergillosis more intensely, if you will, than the rest of us who are not immune compromised. So we recognize the fungal impact and what we need to think about for management. But then we have to think also about those bacteria and virus and the paranoia that we get that those droplet nuclei, under certain instances, can get way out there. They can float and move around, and certainly we recognize that there are the diseases which we have just mentioned that certainly can move about our buildings and create problems. And that's due to the droplet nuclei. The virons that are in that sputum that comes out of our mouths dries up. The mucus dries up quickly, begins to become smaller as it dries and begins to fly. And certainly in slide 18, we see the evaporation time and falling distances of various sized droplets. And if we look at the bottom, we see, and these are old papers that have been worked out many years ago by Dr. Wells, the particles that are discharged at 6 feet and greater than 140 microns tend to fall to the ground. And if the humidity is high, it even falls faster. So if we have particles less than 140 microns, they tend to evaporate into that less than 5 micron particle that becomes our nemesis in the prevention of airborne spread disease. So slide 19 gives us that impression that these things can move about. And certainly that is true and has been documented a number of times in the literature as things move around. And as we talk and do a whole variety of things, we can generate a lot of tissue culture infecting doses, which is a way that we can measure how infectious those coughs and sneezes might be, and the diarrhea part of getting an infectious disease infecting those. I'd be interested in knowing what kind of experience that was to get that into the air, and I'm not going to go into it any more than that. But yet we have to be realistic about what really happens when we do things. As this next slide, 21, tends to make us think, we are so paranoid about it coming back through the air handling system to infect us that we get all wigged out. I worked on the measles issue in California recently, and luckily for them, most of their hospitals are on 100% outside air. Now, that's not the case in my state or in other parts of the world where there are temperatures that are extreme. But when you do that, you get a great advantage. Most of us bring the air back through a filter. And if it comes back through the standard hospital filter, let me tell you, they work very well when they're properly installed and maintained. And there we start to talk about energy. And as the energy issue comes up, we will see the importance of those filters in the management of our infectious diseases, because we want to prevent people from getting paranoid about what might happen on slide 21. So viruses inside of mucus evaporate faster in low humidity levels. Would that be an air-conditioned building? Maybe. So we need to think about making sure we follow our protocols. Our protocols are always important in preventing disease because we can always blame something else. So our personal protective equipment becomes essential. And again, we need to do this in front of the energy management part to remind us of our principles. Our principles are really the fact that the HVAC system will remove and distribute droplet nuclei only if it's not functioning properly. And we have reason to believe that that might be the case in a lot of instances. So indoor air humidity in the winter in the northern hemisphere is low. And certainly where there's high humidity, there seems to be less flu. So we tend to have this experience worldwide that as the humidity drops, there might be more potential for influenza passing. So when we look at what we need to do in the design guidelines for the United States put out by the Facility Guidelines Institute, which just published their 2014 version, some 41 states follow it, what we have is a series of relative humidity and design temperatures that need to be met. Now, we are challenged in hospitals continually by always bringing in more equipment that has more heat gain. That heat needs to be controlled, or our surgeons, our patients become uncomfortable. Why would a patient become uncomfortable? Well, from an infection prevention point of view, if that patient is too hot, too warm, what we have found in some instances is they sweat too much and they can't keep their infection prevention pads for their wound dressings stuck to their skin because they're sweating too much. So we don't want too much heat because that in itself can cause the surgeons to sweat. I've seen some terribly wet surgeons. And certainly we need to maintain these standards. So we have all these ideas. Let's do natural ventilation. You know what? Natural ventilation works. It really does. If you look at slide 25, there are all signs of concepts for natural ventilation. If you want to find a good book on it, the World Health Organization published one on natural ventilation for infection control and healthcare in 2009. Paul Jensen, Dr. Jensen, was one of the lead authors, as was Wing Wong Sito from Hong Kong and others from Tan Tock Seng Hospital in Singapore. And the Asians have a so-called right to natural ventilation, but you have to design it right. If you don't design it right by the methods that are listed there in 25, we run into problems with 26. If you look at the calculations, and I'm not going to go through this, you look at the bottom part, an open window and an open door, you can achieve very high ventilation rates, of course, dependent on the outside air wind movement. But then if you have a 50% open door that goes down, and logically, if you have, like most of our hospitals are designed, an open window and a closed doors, it doesn't work. So while we think we want ventilation, while we think we want to do this, will it comply? I'm talking about the United States today. Will it comply with our HIPAA rules? Will it comply with our air change rates? We are not equipped to do that in the United States, whereas others are. So if we look at the concept, blow it in the front door, blow it out the back door. Keep the windows open and make the air move. You can do that in a circular fashion, a rectangular fashion, but as we go to slide 29, the reality check sets in. Potential application of natural ventilation in ideal conditions. So if we look at hot and humid conditions, hot and dry, moderate and cold, and we look at the stars for performance, we see that a single-sided corridor with natural ventilation has a varied amount of usefulness in a variety of applications. And as you can see moving across that chart, we can see that the hot and dry and the extreme climates are all best served by mechanical ventilation. So does that mean our less acute hospitals can have natural ventilation and our acute care hospitals need to keep mechanical ventilation? I think that's what it's saying. So there are ways, certain climates, that we can take advantage of certainly the natural ventilation. We want as many stars as we can. It's very difficult to achieve a perfect combination in my climate as well as any others. Those closest to the equator maybe have a better chance than others, but we need to be cautious on what type of patient we expose to natural ventilation, because while it may work for tuberculosis, it might not work for protecting our severely compromised host. And that's why we've set up two different kinds of rooms, a pressurized room and a depressurized room for infectious disease management and control. So we look at the slide 31 and see that there on slide 31 we have the infection control parameters, the pressure differentials for a pressurized protective environment, and the pressure differentials for the negatively pressurized airborne infection environment. And those pressures, again, are what's driving the air. And the pressure is truly infection prevention parameter because it controls where things move from a clean to dirty perspective. Always thinking of the patient as either clean or dirty, and clean to dirty airflow would be what we want. And the air change rates, which we'll talk about very shortly, are an essential part of that pollution, if you will, management. The ideal pressures are down below. We only put the minimum into the standard, but the ideal is what we would really want to go for. And 8 pascals is a reasonable amount, but some institutions that I've worked with think they need more, and therein is a rub for energy management and overdoing it for a variety of reasons. So ventilation is really our target. So we have proposed energy efficiencies that include displacement ventilation, chill beams, heat wheels, and minimal leakage for the topics that we will cover today. When we built our latest hospital, one of the very first things we asked for mold management reasons, and unbeknownst to me at the time, energy reasons, we wanted a good exterior wall. So we built a mock-up to make sure we got what I wanted, which was a waterproof wall. And what we did for that was to build this was mocked up down in Florida, and they put an airplane propeller in front of it and a series of a pipe grid that sprayed water when the propeller was turned on onto the surface of that mock-up to see how much it leaked. In addition to that, we heated it and cooled it to see what the expansion-contraction factors were when this surface, this exterior, was exposed to that, again, to give us that really, really tight exterior. Why is that important? We are building a new surgical center, ambulatory surgical center, and it has a combination of normal ventilation with the variable air volume and return air system, which most of us have, and the other is going to have chill beam, energy recovery wheels, and displacement ventilation in place. The goal of this building is to save a lot of money over its lifetime. It, again, is something we're trying here in Minnesota, as I know many of you are doing, and they needed to convince us that this was good for infection prevention. So the benefits of an active beam, reduction of air handling equipment, because you separate the cooling from the rest of the ventilation needs, like minimum outside air. You cut down on ductwork. You get the amount of reheat. Remember how expensive that was. It's quieter. It's improved air quality. Well, it's something we're waiting to see. And we have a reduced risk of cross-contamination, which, again, is something that we are learning to see. This is the building in process. And, again, we ask for that exterior that is well sealed, and you can see a coat of a elastomeric material going over our insulation on this building to make it a well sealed building. And what we find in the literature is that if you are doing energy management, one of the key criteria is to have a well sealed building from the exterior. So that's an important principle. Slide 38 begins to show us what a chill beam is. It looks like a light, but it delivered some air. It's pressurized air into that chill beam. And there are two types of chill beams. One is an active and one is an inactive. We're not going to talk about inactive. That's more or less just air, let air go over it by convection. But we're going to actually move air with a fan through a coil in passive air, or I should say passive beams and active beams. So what we want is to actually move the air through the chill beam by inducing the air in it, because air is being blown through it. And again, that's a ventilation principle. And slide 39 shows a little better the complexity of these. And again, they allow us to separate a lot of that thermal demand that we need to take care of that is done at the air handling system. And in the chill beam process, it's done locally. Now, the chill beam seems to work quite well if we can keep humidity away from it. Why is that a concern? Because if we use these chill beams, they will recirculate air, and they will bring lint into that space. And if there's humidity, you know it's going to condense. So this is something that is going to work 95% of the time in my climate. Occasionally, we exceed those design limits, and we get moisture in the building. But the criteria we put in, it has to be accessible for cleaning. If you clean them once a year, it's going to solve a lot of your problems. You're only going to be humid in this climate, maybe, I think it was 2 weeks, 300 hours a year. We go a little too high in our humidity. So that sealed curtain wall keeps a lot of that out, as well as a good ventilation system. And again, looking at the design in a patient room on slide 40, with the air coming in and getting exhausted through the bathroom, I'm not sure how chill beams will work in a clinical setting. They will probably work very well in a ambulatory clinic setting, but in a patient care, convalescent, regular hospital, we don't know yet. I'm sure they're being built. Again, it's that humidity control that's important. But this would save a lot of money if it achieves the air change rates, the cleansing, if you will, of that air quality that we need with that air change consideration. So we're not sure about chill beams in our patient care setting where the patient spends overnight, but we certainly can encourage it in our clinic setting, not in the surgery center, because there we're sticking with the standard ventilation system. But what about displacement ventilation? What is that? Those of you who've had laminar flow rooms, you blow from one side of the room to the other, you blow from top down, whatever it may be, it's that piston movement, it's that movement of air across a space that really moves the particles with it. And that's a big advantage compared to the normal room ventilation, which just more or less spins the air around. And the reason for wanting to spin it around is it evens out the temperature and humidity and provides comfort. But in infectious disease management, we need to think about control and movement. And in slide 43, you can see a concept slide of air blowing in underneath the bed up to the ventilation system. And quite frankly, we feel that it's very hard to be able to do this because there's so little space in the walls that allow us to bring something down. So how do you bring that ductwork down and deliver it into that space? Hospitals are being built with dilution ventilation, but what I feel, with displacement ventilation, where I feel displacement ventilation has its big advantages in waiting rooms and atriums. So what we found, if on slide 44, with those two diffusers that are on the left side, lower left side, what they can do with that is bring those down with ductwork in a column and deliver the air low at a warmer temperature, which saves a tremendous amount of money. Because if we're delivering air at 55 and now can use displacement ventilation to deliver air at 61 degrees, you save a lot of money and you get an effective infection prevention situation occurring. So if you deliver air low, it warms up immediately and starts to rise. So that thermal buoyance begins to lift the air above the breathing zone. And if we look at slide 45, where we've got a waiting area, you've got some physical separation, and you deliver air low and blow it across that waiting room, it will lift and get out of the breathing zone very quickly, and get exhausted or return through HEPA filters. This is an effective way, I feel, of delivering air to waiting areas so that you don't have to shove the air down only to go back up again or to return the air low. But yet it keeps the air longer in the breathing zone. So displacement ventilation has great potential for lifting air in the waiting rooms, in atriums. Our auditorium, our main venue here on campus, is a displacement ventilation under the seats of our 4,000-seat auditorium. That's been around since the 30s. So it's not a new concept. It's just we haven't been able to figure out exactly how to deliver it to hospital patient rooms, but we can start delivering it quite easily to waiting rooms and atriums in our hospitals. So slide 46. Infection prevention. Rooms may seem warmer due to delivery of temperatures at a higher level. Rising temp creates an upward buoyance. When infectious particles above the breathing zone, it's more than likely safe. Energy management, again, you get warmer air delivered. It lowers energy costs, and it decreases the air exchange for rooms by using 6 feet instead of 8 feet for calculation, which, again, is about an average height. So we do get some advantages there. Disadvantage, difficult to find space in the patient room to deliver the air at a low level. So there are disadvantages. But yet it is would be a good thing for infection prevention in our waiting areas in hospitals. If we look at heat wheels, what's a heat wheel? A heat wheel, it transfers energy from that which we are throwing away to that which we are bringing back into the building to reheat and use down in the patient care areas. So as we discharge the air, we extract either the heating or the cooling from it, and as the wheel turns, it brings that warmer or cooler surface to where the air is coming in as makeup air, and we end up being able to use that energy for good purposes. Now, the trick with heat wheels is to make sure we know which way the pressures are, and that's very easy to do and has been done. So we want to watch pressure. Thinking of clean to dirty, we want the clean side of the air to be going into the dirty side as it's being discharged. And certainly we are concerned that when they clean those coils or when they recharge them, they do it in a fashion that's reasonable. And I believe they thermally clean them up, which really gives us an opportunity to kill what's on those surfaces. The biggest problem that I see about energy misuse in hospitals is that we have deferred maintenance. We don't take care of our buildings. I've seen this worldwide. It's shocking. We have plugged filters. We have temperature control coils that are plugged, duct leakage. Didn't put it together right. Oh, boy. You see dust on fan blades, which really slows the efficiency down, and they don't make sure that the fan belts are slipping in on top of that. They don't calibrate. We don't calibrate our equipment. And what you see that's all covered with fuzz there, and that's a sensing device called a pitot tube that is being plugged with the lint in hospitals. We are huge lint producers, and if we don't keep those clean, we certainly aren't going to be able to manage our pressures, and if we can't manage our pressures, we have, in infection prevention, have something to worry about. We have very large, sophisticated chill water systems in our hospitals, and the temperatures that we have to control with these systems are extremely expensive. Herein lies what costs a lot of money, and the next slide, slide 50, is the connection between the chiller and the cooling tower, where the heat energy is transferred, and what you see is a chiller on the bottom slide and the fins that cause that energy transfer. If they are not kept clean, they do not transfer the energy. So we want to keep our building cool because patients convalesce better when they are cool. They don't need natural ventilation, and we do need to maintain this. Hospitals in the United States in particular have a tendency to avoid doing some of this basic maintenance. But fortunately for us, energy is becoming more and more expensive, so it behooves people to make sure that they keep these things clean to make the buildings more efficient, because as you will see, if we are not efficient, we do not cool, we do not move air, we create problems that might create a potential opportunity for that opportunistic infectious agent to gain a foothold because it's too sweaty, the air isn't moving, or whatever it might be that really blocks our infection control principles. So we certainly see stuff growing on coils. Cooling coils that are not kept clean plug. They develop a biofilm, they develop an odor, and I do have examples in other lectures that I've given where these kinds of conditions have created opportunities for mold growth, odors, and a number of other things that really reduce the ability of the ventilation system to work the way it is supposed to. So what do you do about it? You clean it. What I have found in my years here at this university is that our people are not trained to clean the coils. What's that mean? All you have to do is squirt them. Well, what I've, from the vendors that have approached us in the last few months to a year, we are finding that if you can get our coils clean, we can move more air through them. If you can move more air through the coils, one, it enhances cooling. Two, it keeps the air change rates properly, and it does give us a better chance to provide patients with a better environment in which to convalesce. So what we have seen on one small coil that we cleaned last summer, 160 pounds of dirt came out of it. And that prevents that energy transfer, that it prevents all the things that we talked about from moving air through that. So if we can clean our coils in the manner that they're supposed to be cleaned, and that takes a certain amount of professional experience, we can benefit. And that certainly will save energy, it will save money, and potentially it will give us better infection prevention results. Filters are the same way on the slide 53. When you got them plugged that bad, it's not going to move air. It's pathetic when that happens, but it does happen. I'm not going to go into my case histories today, but they keep popping into my head, so I'm going to restrain myself because I'm running out of time. And certainly we can show examples where decreased airflow can create problems within the building, because slide 54 is all about air change rates. If we can move air, if we can keep those air change rates up there, we can get rid of 90% of the particles in the air in just 12 minutes with the 12 air changes per hour. And the graphic on the right really shows that in a visual manner rather than a numerical. And certainly that point of diminishing returns out around 12 and 15 is more readily met when you've got the air to be able to accomplish that task. So keeping the coils clean, making sure that that is working properly is a big factor, and we are slowly beginning to address that at my institution. But, of course, they're short of money, and you only can do so many at a time. What really happens when you have a need for air? And again, a case history pops into mind, which I'm not going to mention, where they've actually removed filters or opened doors after the filter bank to get a sufficient amount of air to deliver downstairs because they can't get it any other way. And what does that do? It takes away the filtration efficacy, and I have seen a heart transplant program go south because of that some years ago. So we really don't want to tempt any of our mechanics, any of our systems people to say, I can't stand the complaints, they're too hot in the operating rooms, I'm taking the filters out. Oh, my God. You wouldn't think that would happen. Guess again. You wouldn't think that would happen, but it does. So we have to make sure our filters are working properly. There is a big push across the industry to get low-pressure drop filters. Filters generally work when they're properly installed and maintained. We need to be careful because I have run into filters that make a claim and they don't work. So we do need to make sure that we have good filters that are installed properly. And slide 56 demonstrates some of the filter theory where the very small particles are removed and the very large particles, those greater than 1 and those less than 0.01, are removed with greater efficiency. Why? Because impaction, diffusions, and interception and are all part of how filter theory really works to capture those particles. The problem is, in the next slide, filters aren't properly installed. I've seen this so much across our country in the United States, where we go and install the filters, spend a lot of money, and then we don't see it. This was a Chicagoland hospital from some years ago. Everything looked good through the window, but my particle counter did not demonstrate a good filtration. I asked them to open it up, and sure enough, the filters were ripped out in the bottom. So we certainly want our systems to run efficiently. We want them to run effectively by having filters properly installed, because that's the balance we want. We want to move air, but we want it to be filtered before it reaches our susceptible populations. And what I found, and this is not an approved method, I have found by simply taking a particle counter, slide 58, and putting across the filter bank, I can see huge differences. You have to be careful. You have to develop a technique. You don't want to suck the dust from the insulation and in that air balance hole into the particle counter, because it will ruin the optics. But yet, you can see before and after the filter that we have very efficient filtration from this Pennsylvania hospital that I tested a few years ago. When we look at the Joint Commission, they inspect us. They find that the built environment and the utility systems ventilation received findings of the most common building-related findings that are out there. So we do need to be aware of that. We do need to pay attention. And certainly the Joint Commission was here not too many weeks ago. They certainly did pay attention and ask questions about the built as well as the utility systems in our hospitals. The depiction of the hospital with the loading dock and the plumbing repairs and the demolition demonstrates that we have air moving all sorts of ways in our buildings, especially if we don't pay attention. Some of us have to pay attention because we're dealing with large populations of compromised hosts. So while we want to accommodate everything, we do need to be careful when we start exhausting our building or when we start doing a whole bunch of things in the name of infection prevention during construction. We need to think harder about that as we move forward, because those of us in extreme climates will pay bigger penalties if we don't pay attention to the way our building is sealed and the way that air moves in and out of these spaces that are nicely depicted in this graphic on slide number 60. One of the reasons why that's important is because of what I saw on an East Coast hospital last year. Room 206 housed a child with severe combined immune deficiency. For whatever reason, that hospital put that child in that room under negative pressure. And what we see essentially is that with that, and you probably can't see that, most of you are looking at a piece of paper, that the supply air was less than the exhaust. In addition, when the door opened up, that was even less than the total exhaust. And what ended up happening was that air came in around the mullions on the windows. The slide with the picture with somebody holding a smoke stick, if it were animated like I was hoping it would be, it would show the air streaming into that space. They had no business putting a child in a room like that that was immune compromised. But again, it only shows that there is a lack of understanding of what needs to be done in our hospitals. And if they can't get this right, how can they get the energy part right? Because energy really drives a lot of costs in our buildings, and certainly that is something that we need to really understand from a ventilation point of view in order to protect our patients, our most susceptible patients, under those circumstances. And a lot of that has to do with how much the rooms leak. How sealed should we make our buildings? If you look at a typical patient room like you see in slide 63, there's all kinds of potential for leakage, from the air handling HVAC systems coming in to plumbing and electrical above the ceiling. If we don't seal it, we have problems. And what I'm fortunate for is I live in a very cold climate, and up here in Minnesota, it makes sense to protect us from the cold, and one of the ways that they've learned to do that is to develop a technology called a blower door. We set up a blower door. Minneapolis Blower Door is a company here that makes these fabric doors, and as you can see in slide 64, you can hook it up on a room door and have a blower fan, and with that fan you can manipulate the volume of air going through it with a pressure gauge and a computer. You can determine the leakage in the room, and if in slide 65, we set up our isolation rooms and tested with this duct blaster blower door and determined through a computer program that's put out by the company that our isolation rooms had quite a bit of leakage. This means little to many of you, but it's 22 square inches per 100 square feet. Now, in Canada, the standard for a weather-tight home is 2.5 square inches of leakage per 100 square feet. There's nothing like that exists in healthcare, nothing. When we sealed our bone marrow rooms, not knowing what we were doing, we sealed them to the point where we got very good leakage control. So there is no standard for that, and the only standard that I have seen is one that's put out by the CDC, and they say you should have a half a square foot of leakage per room. Now, I don't know what that means either, but by the same token, on the next slide, what we learned was we brought in the owner of the Minneapolis Blower Door, Gary, and he brought in a group of weatherization specialists, and we brought our trade union supervisors in, and we taught them on the upper right-hand corner how to seal a room based on the computer graphics that you see down below. Every time we sealed, they could see the improvement. Every time we closed off a vent, they could see the improvement. So that when we built our hospital, I asked for 300 sealed rooms. What does that mean? The demising walls and the sound barriers are all sealed. All of our electrical conduits, all our electrical lines that come into the rooms are sealed. We seal the windows. We seal a whole variety of places in the name of barrier management. I must say that Hilti sponsored a study that I'm going to talk about, and it has to do with what we should be thinking about, and probably the easiest thing we can do for energy management in our hospital is to seal the rooms. So we have 4 points to make: infection control, sound management, energy movement, and UL, life safety issues. So what does that mean? Well, in our day, when you are dealing with something like a high-level infectious unit, fondly called the Ebola unit, in this depiction on slide 69, I'm working with a hospital in another part of the world where they want these precise control measures in their rooms where they're going to be treating that highly infectious agent. And when you look at slide 70, there's a need under these design criteria for very strict pressure management. Very strict pressure management. How can you maintain pressures like this was exactly the questions I asked these people, because they didn't know what I was talking about as far as a sealed room was concerned. And I say, how do you certify that? Well, we don't do that in this country. Well, yes, you better start doing that in that country. But when you start wanting these kinds of pressure management issues, you better have a good plan on how to seal that space in order to make those pressures work. Otherwise, you're going to be freaking out, wondering who's been exposed and dealing with all of that kind of publicity under those circumstances. In the next slide, another place where we need to be very careful about sealing the space and making sure it's good is in a construction project. This was in a very large city pharmacy where they were manufacturing chemo, protective, a variety of other chemicals that they were going to inject, and they wanted strict pressure management, sealed spaces between the workspace and the manufacturing space for that particular product that they were making. So I see that at my institution, and I see the problems we have if the space isn't well controlled. So what we did was we engaged the Carpenters Union, and through the work of Hilti, we set up a mock room. That mock room had was built like any building or room would be built, with holes from the, if you will, the upper deck to the walls, and from the floor to the slab below. And we set up our blower door or our fan in the system, and we tested inside 73 a whole bunch of different penetrations that come through the wall in a typical room, no matter where you are in the world. These things come through your wall, and fire code, being the boss code, dictates that we seal these up. And so what you see in the next slide is a whole bunch of seals on a variety of things that come through the wall. Now, if we did not pay attention to sealing these, we would not have control in those rooms, even with the ceiling tile in, because the penetrations, you think how many utility boxes there are in a patient room, especially in ICU. And what you see on the upper slide, if you will, upper part of this, testing penetrations, you see a wrap around one of the electrical boxes instead of the mud that I was putting around in a previous slide. So we tested every one of those openings, and suffice it to say, we could demonstrate, and I'm not going to go through this, we could show that there was a significant decrease in escaping air with each one of those gadgets that we put through the wall, open and then closed. So it's you can see open bottom of wall, sealed bottom of wall, open plumbing, sealed plumbing. All of them made a difference. So what we're pushing is to seal the room. What benefit do you get from that? You get better life safety. What does life safety mean? Fire management, smoke control. If our rooms are better sealed, we can get better safety measures for our fight and what is it? I can't remember the term we use. You control the space and you escape horizontally, but you combat the fire in place because it's very difficult for us to evacuate a hospital, and we need to control that smoke because fire doesn't kill, smoke kills. So we get one big benefit by having a sealed building is to have better life safety. The other thing which fascinated me was I asked for 30 rooms out of 100 to be well sealed and blower door tested. When all came to shove and everything was done, the guys told me from the construction company, Andy, we didn't test 30 rooms, we tested all 100 rooms. I said, what did you do that for? And they said, for HIPAA. I said, what? HIPAA, sound management. How does sound transfer? Sound transfers on air. So it moves through the air in South Minneapolis at the end of the big runways there. People who live there can have their houses tested for leakage, my son, so that they can seal that house to prevent the sound from those big jets flying over the house. The same principle applies in our hospital rooms. If we seal the room, we can prevent that sound from transferring. I go to some of our clinics, I can hear the people talking next door because the air there is a passageway around the mullions on the windows of that particular building. So what they did is they sealed all 100 rooms in that hospital so that we could get better sound management. In addition to that, because the rooms are sealed, there is less need for heating and cooling because the air does not escape. One of the untold consequences that we had for our hospital when we built it was, especially on bone marrow, our bone marrow ward, which was 26 beds, what we ended up having is we couldn't close the suite doors. The doors to the unit would not close. Why? Because the air was not leaking away. The air, when they design a hospital or design most buildings that have mechanical systems, they design in a leakage rate. Well, if you eliminate that leakage rate, where's the air going to go? Well, it was trying to go out the front door and couldn't close the door. So how do you solve that problem? You return more air to be reused. What does that save? Energy. That saves a lot of energy. So that is something that is very useful in this concept. And, of course, last but not least, and everybody wants to put infection prevention first, it does help with keeping the building drier. We don't get leakage from that point of view. In addition to that, because we have control of our ventilation on those isolation rooms in particular, you don't need to work up so many people that might have exposure potential. contact tracing is difficult, especially when you've got a positive pressure room that's supposed to be negative. Then you have to look at a lot more people than if it was working in the first place, and the sealed room gives us a better confidence, a more assurance that, in fact, we do have what we want in that space. So we really get a four-fer. We get 4 measures for the price of 1 if we seal the room. We certainly saw that we can get some savings by changing out some of the ventilation systems to chill beams or in certain instances, or even displacement ventilation. We want to embrace as many of those ideas as we can without being cavalier, but it looks like the really true way of doing it is sealing the room. So when we look at infection prevention and ventilation, we really recognize that air volumes must be maintained to make sure that we can clean the air of contaminants. Remember the controlled hazards from odors, gangrenous skin. Oh my God, I didn't like the smell of that. To controlling the aerosols that are being generated when we give medicated aerosols, to even the control of the through dilution ventilation, spores that may come off of our bodies that we shed into that environment. So those air volumes should be maintained, and we can do that by making sure that our facilities, through a team effort, and infection prevention is involved with a lot of decision making at our institution, and we certainly want them there to be able to show that having good ventilation management will in fact benefit for a lot of different reasons. Again, impediments of plugged equipment that need cleaning or changing out of filters are all important. I don't want to see us just go strictly on the fact that there are pressures, because I saw a situation in the middle of the United States at one time not too many years ago where a patient got an infection during surgery, and when they investigated to see what happened, because it was a tragic infection, they found that they had not changed the filters in 3 years. Why? Well, the pressure didn't change. Why? Because they had bypass. So while we really want to optimize how we take care of our filtration systems, we have to make sure they work properly. Otherwise, they won't benefit us in getting us a disease-free or secondary disease-free situation in our hospital. So aspiring to have good air quality requires routine maintenance to ensure air changes per hour, filtration, and pressure. We can't get sucked into things that are not tried and true. And certainly, we've talked here today about some measures that can benefit, and I would encourage it, especially the aspect of retuning your building, making sure your building is working properly. That recommissioning of a building will make it all work the way it's supposed to, because so many of our buildings get out of tune so quickly. I know all too well because I work with them often in my own institution. So with that, I hope this has been informative to all of you. I think I have no time for questions and answers, but I would encourage any of you to ask questions that can be forwarded to me, and I would be more than happy to deal with that on a email basis. I have a terrible time with telephone because I'm in a hole most of the time in these big buildings. So I appreciate the opportunity to speak to you. I hope it's been useful, and thank you and good day.
Well, thank you, Andy, for a very, very informative, comprehensive lecture. I learned a lot. I'm sure our audience did as well. Let's go to the slide that follows Andy's last slide. This will give you a listing of some of the upcoming teleclasses for the next month. Some are free, some are from the British teleclass series, and lots of good topics there. So do join us again for some of these other presentations. If there are questions from the audience, as Andy indicated, you can contact him directly with his email address on his last slide, or you can send them to info@webertraining.com, and the staff at Weber Training will forward them on to Andy. We thank you all for attending today's lecture and hope to have you join us again. The very last slide on your slide list gives the general sponsors for the teleclass series, and we thank Sealed Air, Virox, and WHO for their continued support of the Weber Training teleclass. So for now, goodbye until the next teleclass. Have a great day.